Hi, my name is Nicholas Dwork, and today we're going to be discussing some preliminaries that'll help us out with our discussion on magnetic resonance imaging. Here I'm showing a 2D array, just a 2D grid of numbers. Now I could change the way I'm displaying this array. I could make 0 black and 255 white, and each number in between some level of gray that's darker or brighter based on which number it is. Here's that depiction. So rather than showing the numbers, we can show corresponding colors. I can show more numbers as colors. Here's a larger array. We can always go back to the numbers or represent it as a grid of gray squares. Let me make the array larger and larger and larger and larger. At this point, our eye can no longer discern most of the individual pixels. And so what I've just shown you is that an image is nothing but a 2D array that's displayed on the screen in an interesting way. An image is also a vector. One way to see that an image is a vector is just to concatenate the columns into a 1D array of numbers. And since we know the size of the image, we could go back and forth from this column to the image, no problem. A color image is just 3 2D arrays, one representing the red, one representing the green, one representing the blue. And on the computer, there are little pixels that show us a certain amount of red, a certain amount of green, and a certain amount of blue so close that our eyes can't distinguish the different sources. Here's a special type of image. This is a cosine. This is a diagonal cosine, so it's a cosine in both the horizontal and the vertical directions. Here's a different cosine. This one has much less of a frequency, and you can see that it's brighter at the bottom, it gets darker near the top, and then it starts to rise again. I'm going to sum up several of these cosines together. So I'm going to keep the individual cosines on the right and the sums on the left. So here I'm just summing this first cosine. Now I'm summing the one you just saw with the one that's currently on the right, and you see the pattern that it creates on the left. And I'm going to do this a lot for many different cosines, and we'll see what happens. Currently I'm adding one cosine at a time. Very soon I'll jump and add many cosines together. I'll only show you every 10th cosine or so that I'm adding, and then maybe every 100th. As the cosines get thinner and thinner strips, those are higher frequencies. And hopefully you get the point. By summing up these cosines, we're reconstructing the image of the dog eating ice cream on the left. And so what this is showing is called the discrete Fourier transform. Now what I showed you was a real image previously, but you could have complex numbers in each pixel, and then you'd have a complex image or a complex vector. The discrete Fourier transform says that any vector capital G can be represented as a sum of complex exponentials, as shown here. The little g shows the weight of each complex exponential. Now recall that a complex exponential is just the sum of a cosine and a sine according to Euler's formula. This summation can be represented as a matrix multiplication. So if we let the summation transformation equal f, then capital G is equal to f times little g. And this matrix is invertible. So if we have capital G, we can recover little g by multiplying capital G by f inverse. Thank you for your attention.